where oil really comes from, why the Middle East and Venezuela have so much oil. Many people grew up hearing a simple explanation in school. Oil would come from dinosaurs. The image is easy to imagine. Ancient forests, giant creatures, everything buried during eras being slowly converted into fossil fuel. At first glance, it even seems to make sense. Enormous animals, enormous quantities of oil. Except there's a serious problem with this story. It doesn't add up. Even if every dinosaur that ever existed had been completely transformed into oil, it still wouldn't be enough to justify the colossal volume of oil that has already been found on the planet. Not by a long shot. The combined biomass of all dinosaurs was too small when compared to another form of life that existed on an almost inconceivable scale. Something minuscule, almost invisible to the naked eye, but present in absurd quantities. And that's precisely where the real story starts to get interesting. Over vast periods of Earth's history, shallow seas repeatedly invaded large extensions of the continents. Regions that today are deserts, mountain ranges, or dry areas were once submerged for millions of years. In these ancient marine environments, life flourished intensely. Still, oil is not distributed uniformly across the globe. On the contrary, it concentrates in an impressive way in only a few regions, while vast areas of the planet have very little or almost nothing. That's why the most important question is not simply, where did oil come from? The truly decisive question is another. Why did it form in large quantities only in certain places? If dinosaurs were never the main origin, then what was? Scientists have been investigating this since the 19th century, since the first geologists noticed a recurring pattern. Oil almost always appeared in rocks formed in ancient marine environments. Over time, two very different explanations gained prominence. The first is the scientific view predominant today. In it, oil is the result of the transformation of ancient life, not dinosaurs, but microscopic marine organisms such as plankton, algae, and bacteria. They were beings so small that millions of them could fit in a single drop of seawater. Still, over millions of years, these life forms lived, died, and continuously sank, accumulating at the bottom of shallow seas in successive layers. But there is also an alternative hypothesis, much less accepted, yet historically important. In the 1950s, Soviet geologist Nikolai Kudryavtsev suggested that oil could form in the depths of the Earth from extreme heat and pressure without directly depending on organic matter. Later, astrophysicist Thomas Gold expanded this idea, proposing that hydrocarbons could arise in the Earth's mantle and slowly migrate through deep fractures in the crust. This proposal became known as the abiogenic theory, the notion that oil could originate without the participation of life. We'll return to it later because it raises an important question. Even if this process exists to some degree, would it be capable of explaining the enormous oil fields upon which the world depends? Before that, it's worth looking at the oil map and understanding who are the major geopolitical protagonists. When we observe where the largest proven reserves on the planet are located, some areas stand out incontestably. The country with the largest proven reserve is Venezuela, with more than 300 billion barrels, much of it concentrated in the immense Orinoco Belt. However, when we broaden the analysis to entire regions, the largest concentration of conventional oil appears around the Arabian Peninsula. Saudi Arabia, Iraq, Iran, Kuwait, United Arab Emirates, and Qatar, together, concentrate a gigantic portion of world reserves. Beyond them, Russia, Canada, the United States, and the North Sea region also play a relevant role. The curious point emerges when geologists reconstruct how these regions were hundreds of millions of years ago. Then a very clear pattern appears. Large areas of what today corresponds to Saudi Arabia, Iraq, Iran, Kuwait, United Arab Emirates, and Qatar were already covered by shallow and warm seas connected to the ancient Tethys Ocean. Northern South America, especially Venezuela, also developed extensive sedimentary basins associated with ancient marine and deltaic environments. But the puzzle doesn't end there. Africa, Australia, parts of Europe, and different areas of the Americas also had ancient seas. So why didn't all these regions end up forming gigantic deposits? Why did only some become oil superpowers? Would it have been just geological luck? What, in fact, made the difference? The answer begins with trillions and trillions of microscopic organisms, plankton, algae, and bacteria that lived on the surface of these seas, died, and slowly sank to the bottom. In certain parts of the ancient seas that covered what is now the Middle East, there was little oxygen at the sea floor. This was crucial. Instead of decomposing completely, much of this organic matter remained preserved. Layer after layer, it was being covered by mud, sand, and other sediments. Over millions of years, these sediments accumulated until reaching kilometers in thickness. The deeper the burial, the higher the temperature. This occurs because the Earth's internal heat continuously flows outward. On average, temperature rises about 25 to 30 degrees Celsius per kilometer of depth. When this organic material becomes buried between approximately 2 and 4 kilometers, it enters the so-called oil window, generally between 60 and 120 degrees Celsius. In this range, organic matter first transforms into kerogen, a waxy substance. Then, with more heat and pressure, this kerogen breaks down and generates liquid oil and natural gas. There is, however, another stage that usually surprises many people. Newly formed oil is less dense than the salt water present in the rocks. That's why it tends to migrate upward, driven by buoyancy. It can cross microscopic pores and small fractures for hundreds or even thousands of meters. But this upward movement is not enough to create an exploitable oil field. For that, two conditions need to act together: a geological trap and an impermeable sealing rock. The trap can be, for example, a fold in the rock forming a kind of natural dome. The sealing layer can be shale, salt, or very compact clay, preventing the passage of oil. It's this rare combination of generation, migration, entrapment, and sealing that explains why only some sedimentary basins on Earth became giant petroleum provinces. And the story becomes even more interesting when we realize that not all oil is the same. Even when it forms through similar processes, its quality can vary enormously from one region to another. These differences influence price, ease of refining, strategic value, and even geopolitical relations. In Saudi Arabia, for example, much of the oil is of the light and sweet type, with low sulfur content. It flows with relative ease and costs less to refine. Already in the Orinoco Belt, in Venezuela, the oil is much heavier and acidic, with higher sulfur content. In many cases, it behaves almost like tar. This happens because underground processes, including microbial action over time, can degrade the lighter fractions, leaving a more viscous and difficult to process oil. Because of this, specific refineries, such as several facilities located on the coast of the Gulf of the United States, were designed precisely to deal with heavier and dirtier oils. Now we come to the big question that always comes back. After all, could oil really form in the depths of the Earth without the participation of life? The abiogenic theory suggests this possibility. If it were the main explanation for large commercial fields, then it would be reasonable to expect enormous deposits spread more widely, including in deep crystalline rocks and in places unrelated to ancient seas. But that's not the observed pattern. Almost all of the world's largest oil fields appear in sedimentary basins that contain thick layers of rock rich in organic matter formed from ancient marine environments. And the strongest evidence perhaps lies in the oil itself. Scientists find within it special molecules called biomarkers, such as steranes and hopanes. These substances function as chemical fossils. They are molecular traces that relate directly to the cell membranes of ancient algae, bacteria, and plankton. The structure of these molecules corresponds remarkably to compounds produced by living beings. There is not, as far as is known, a deep geological process capable of generating on a large scale these complex chemical signatures so associated with life. The carbon present in oil reinforces this conclusion even further. The carbon element exists mainly in two stable forms, carbon-12 and carbon-13. Living organisms tend to prefer carbon-12, which is lighter and easier to use in their biological processes. That's why organic matter produced by algae and plankton becomes enriched in carbon-12. When scientists analyze oil, they find exactly this same isotopic pattern, a clear predominance of carbon-12. This compatibility is a powerful clue that oil derives in large measure from ancestral organic matter. Thus, we have three independent lines of evidence pointing in the same direction: the type of rock in which oil is found, the biomarkers preserved in its composition, and the isotopic signature of carbon. Together, they indicate that the vast majority of the planet's commercial oil originated from tiny ancient marine organisms buried and transformed by heat and pressure over millions of years. But what about the idea that oil would be constantly renewed in large quantities in the depths of the Earth? Small hydrocarbons can, yes, form today through natural chemical reactions in some environments, such as submarine hydrothermal systems. The problem is the scale. These quantities are minimal when compared to the gigantic fields that supply the global economy. Large commercial deposits required colossal volumes of organic matter accumulated during immense geological intervals. On the human timescale, this means one very simple thing. Oil is, in practice, a non-renewable resource. Even if abiogenic hydrocarbons exist in small quantities in nature, they do not explain the enormous commercial reservoirs upon which transportation, industries, and entire economies depend. In the end, the real origin of oil is not in giant dinosaurs, but in countless microscopic organisms that lived in ancient seas, were preserved under very specific conditions, and then slowly transformed by the forces of the Earth's interior. And the reason why certain regions, like the Middle East and Venezuela, concentrate so much oil is not a single isolated factor, but the extraordinary combination of several elements: productive seas, low oxygen levels at the bottom, adequate burial, right temperature, efficient migration, and geological traps capable of retaining oil for millions of years. In other words, it was not enough to have marine life. It was also necessary that the geology cooperate almost perfectly. And it was precisely this rare coincidence of conditions that transformed certain parts of the planet into decisive energy centers for modern history.